So what do? Next step. Well, you throw in your favorite kind of noise right there. And you hope that that's going to scramble everything up. And you can do that. And this is what happens when you do that. So this is a network of 100 cells. And they each have their own noise sources, which means that they're all getting their own specific synaptic input. So this cell's noise is different from this cell's noise. It's the same statistically, but it's different random numbers. Okay? So these cells are therefore being stimulated, but depending on the geometry in the experiment, you either stimulate one cell or you stimulate everybody. So this is what's happening. If these cells are firing on their own, even without stimulus, you record, they're firing already. Why are they firing? Well, they're getting synaptic input from the brain, okay, and from the receptors. They're constantly getting something, so they're firing. But they're firing very randomly. So it's a bit like a random carrier. From, in radio theory, you have some kind of stochastic carrier, and on top of that, you have to detect changes. Okay? That seems to be the way the system is wired up. Now, if you add an extra source of noise to only one cell, well, this is lost in the sea of fluctuations that are already occurring in here. Everybody's already firing randomly. So you add one more input that's noisy, you don't see much of anything. So this produces autocorrelation functions which are like the data. There's just not much structure to it. If you take this out, you don't see much change. Okay, I'm not showing you that, but it's not going to change much of anything. Now, the trick is what happens if you do this. And I'm stimulating everybody in parallel with the same waveform. The waveform is random, but everybody gets it. So now you're introducing correlations between the cells, right? For example, when this event comes down like that, everybody gets hyperpolarized. So everybody slows down their firing. And after that, everybody starts up again. And this is kind of generating then waves into the system because they're correlated. And now you can start seeing patterns. If you've got a bunch of cells that fire together, this is going to propagate up, and then it's going to come back and do stuff. And this is a negative sign. This is going to create, you know that's going to create a wave. It's going to create an oscillation. So sure enough, this is what happens. You get this autocorrelation that has an oscillation in it. So simply by changing the geometry from that to that, you get the oscillation. I should mention that the amount, the firing rates of the cells is the same in both situations. If you were to record this cell with the global input or the local input, it's the same. So you're spreading the input out to everybody. Okay? So it's really, the dynamics has been pushed into another regime. So it's very similar to the kinds of oscillations we see in other neural nets, like what David was talking about this morning. So you get Hopf bifurcations and rate models with delays. Right? Yeah?
Yeah. The time scale of that modulation should be comparable to the delay or not?
Yeah, so roughly Hopf bifurcations for a simple delay equation gives you a time scale of about 2 delays. That's about the period. So you can work all that stuff out analytically to some extent. I'll give you an idea in a minute. Okay, this is another experiment. It's a bit of a variant on it. We just put a bunch of dipoles, and each dipole emits a noise, and also there's a global noise. So this is a very popular topic these days. Yes, Axel?
So we explained very nicely why you get this oscillation, but why do we have still the lower peak? Is there also an idea?
This one here?
Yeah, why is it still there?
Yeah, it's because basically you have a process that's kind of firing away. Sometimes there's short events, okay? But if you modulate the whole thing with some kind of internal wave, you're still going to get some kind of few events down here, but now they're going to be more separated. So these produce very short intervals. These pile up here, okay? We also know that these cells burst. I gave you a plot like that yesterday. They have this bursting pattern, and that reinforces that peak. Okay? But right now the model has no bursting. But we tried it with bursting too, and it doesn't change the story qualitatively. Okay? Any other objections, thoughts? Okay. So this is an example where we can smoothly change. Instead of going from bug to whole fish, we just go gradually. We can have the same input to everybody. So there's a global input. Everybody gets the same noise. Plus everybody gets their own noise. This is shared noise. It's a pretty popular topic these days. And there's a parameter C that allows you to go from one to the other. Either every dipole is just its own source of noise, or they're all doing the same thing together, and you can change that parameter C. So you can think of the parameter C as the degree of spatial correlation. How much are things correlated in space, coming in concert to stimulate the input? Okay, so I'm going to derive some equations to get at one quantity, which is the spectrum. I want to know what frequencies are going on in this system. I have a single cell recording. I have a bunch of spikes. I want to get the power spectrum of that spike train. I want to know what frequencies are in there. That's the goal. So, and I want to do that as a function of this parameter C. Okay? Is C going to be, C, as C goes from local to global, you should go from no oscillation to oscillation. Let me go ahead and show you what the data looks like first. Data looks always very messy. Okay? Here's the power spectrum as a function of frequency. Now look what's going on. There's C equals 0, you get a peak over here. C equals 1, you get a peak over here. A bit higher than this one. But what we see is that the black is basically going to the red and then to the blue. So as you're increasing the correlation in space, you're producing this power more and more in the gamma range over here. Admittedly, this peak we don't quite know where it comes from. It's not going to be in our theory, and I'll show you the theory in a minute. Okay. So here's, well actually here's the result of the theory. I won't have time to go into the detail. The theory shows you this. You go from a rather flat line, actually this is like showing you just this part. You go from a flat line to something that has a nice peak. Okay? So as I change that parameter C, which is spatial correlation, if I correlate things in space, this nice peak shows up around the frequencies we observe experimentally. These are numerical simulation points of the theory. Okay? So, and this is the theoretical